So I have been coming to this workshop for many years, since 1998 as it turns out, because I went and looked back at what I've been doing. So I did start with an overview of where we were about 20 years ago, and then going all the way to today, how things have evolved since then. So there were certain issues we were talking about back then. The computers were changing to a new technology. Back then it was parallel computing, now it's something called heterogeneous computing. Each time we were facing a lot of challenges. So we were trying to say what are the new approaches we're going to take to deal with the challenges. And one thing is that the science is also getting much more complex. So in terms of global warming, the basic result that if you increase and the humans put more CO2 into the atmosphere, that's going to warm the planet. That's been known since about the 60s. But then people want to know more and more detailed things. So an example I gave is people in India care about the monsoon. So they want to know what's going to happen to the monsoon. And it turns out in order to correctly model what's going to happen to the monsoon under global warming, it's not enough just to put CO2. You also have to know about other things called aerosols, which is like sulfates and dust and black carbon and so forth. You need to put those into the atmosphere as well. So the models are becoming more and more complex, to the point where no single person understands the whole model. So some people know about the chemistry, some people know about the physics, some people know about the oceans, some people know about the biosphere, and you have to build a system where all of this works together. And secondly, we are increasing what's called the resolution of the model, where we're trying to make it appear at finer and finer scales. And when you do that, you can start resolving first big storm systems like hurricanes. And as you keep increasing it further, you'll start to resolve individual clouds. And each time we do one of these things where a new phenomenon which you could not see in your model, let's think about it as a camera, which is where things are coming into focus. So first the storms come into focus and the clouds come into focus, and each time that happens you understand a little more about the system. And all of these things are computationally very intensive, so you have to learn to use the computers really, really well. So that's sort of the work that I do. One is, there are two or three things I'd like you to take away from the talk. One is that the climate models are getting very complex, and therefore it requires fairly specialized ways of using them on computers. A second message I would like to take away is that the hardware, the computers themselves are becoming more and more complex as well. So there is this difficulty now between matching what's going on the modeling side, the science we want to put in, and then the computers themselves. So there is this gap there that we are trying to fill, which in my talk I refer to the jaws of code complexity. So it's like the codes are getting complex and the hardware is getting complex, and there's something that we have to do in between inside these jaws. So a lot of the work is going in there. But the fact is, as we use these things more and more, the second message I'd like to take away is that the understanding that we have of the system is indeed improving. A second message is that there are a few areas where we don't quite understand how to model the system. There what happens is that different modeling centers around the world try different approaches. And what we do these days is that we try to run the same experiments. So when one modeling center says, I have a nice, cool way I've discovered for representing clouds, and somebody else has a different way, we have ways of comparing the results across these models. So that is the second thing we do. The third thing I want to emphasize is that how important computers are to this high-performance computing in particular, because if you think about it, there is only one planet, and you don't want to be doing experiments with the one planet. It's the one planet, I'll emphasize, that the only planet we know in the entire universe that supports life, carbon-based life at least, as far as we know. So you don't want to be messing with it. So the only way you should be experimenting with the system is to build a model, a simulation of the system, and do all your experimenting there. So I think that's the third key message I'd like to get across, how important computing is to this whole enterprise. No, as I said before, we don't want to be experimenting with the real system. In medical research and so forth, when we are trying out new things, we often try it out on a population of patients. So we run these clinical trials. Here we have a patient that possibly has something going on which is not very good, and the only way you can experiment with it is by simulation, because there is only one patient, so you cannot really do the experiments on the patient. So it's extremely important that we use computing for that. And the computers that we have to use for this problem, as far as we know, because the system is so complex, is the biggest computers we have available today. So right now I would say they're very, very closely linked. Climate science as we do it today cannot be done without big computing.